Okay, well, it is the half hour. It must be lunchtime somewhere. I'm Geoff Bauer. I'm your moderator for this session. I'm with ASIAA. I'm based in Hilo, Hawaii, where it is definitely not lunchtime. I'm very pleased to introduce Mark Reid to give this special lunchtime talk. Mark is one of the most distinguished radio astronomers in the United States and in the world, a recent newly elected member of the National Academy of Sciences, and has been involved in VLBI since its very early days, and has made seminal contributions throughout the decades. And so today he's going to tell us about M87, Sag A*, and micro-arcsecond astrometry. So take it away, Mark.
Thank you. Please consider this an after dinner talk, and if you're in the right time zone, pour yourself a glass of wine or brandy. It's going to be basically a bit of history and culture, so should be pretty fun and simple. So I'm going to first start back in the 1970s. I actually started doing VLBI in 1971, and pretty early on I got interested in M87. And so actually the early history of VLBI is very similar to the early work and current work of the ngEHT. We definitely started with typically 3, maybe even 4 telescopes, because it was just a lot of work to do this stuff. You had to go to all the sites, as ngEHT people have done. We had to bring back heavy magnetic tape from each site, take it there and bring it back. And then we had to correlate it very slowly, usually one baseline at a time. And so, yeah, we started with 3 or 4 stations. And then just like the ngEHT, we wanted to get better UV coverage to get better imaging. And in 1979, a group of us proposed an 8-station VLBI observation at 18 centimeters wavelength. And here's a list of the telescopes that we used. A lot of the sites are still in use. Many of those telescopes, most actually, are not being used anymore. And it's kind of fun to look at the column labeled frequency standard. You'll see besides some hydrogen masers, there's some rubidiums and even a crystal oscillator at the VLA site. And the receiver types are also pretty interesting: parametric amplifiers and field effect transistors, none of which are used anymore. So I led the M87 observations, and this produced this image, that array at 18 centimeters. You can see the scales in milliarcseconds, so it's about 20 milliarcseconds per tick mark. That's kind of a big scale. This was a pretty good image for the time. It showed that it was a one-sided jet. You could trace that jet for about 50 milliarcseconds or so above a brightness of 10 to the 8th degrees. And you could tell there was no counterjet to some limit. And you could also tell that the position angle of the jet exactly matched the very large scale 20 arcsecond jet seen in radio, optical, and even X-ray images later. So if the absence of the counterjet was due to Doppler boosting of the jet and deboosting of the counterjet, that required that the jet was within about 60 degrees of the line of sight and had to have a bulk flow speed of about 60% the speed of light or faster. There was no real bending of this jet seen, although there was some hints of wiggling, which you can sort of see in that image. Well, this actually got us to start thinking bigger. And so in 1983, there was this great VLBI meeting at IAA Symposium 110 in Bologna, Italy, where the food was great, the wine was great, the spirits were great. Everybody had a very good time. And so I remember we were after a really good meal and drinking stuff. A lot of us got together and asked, how many antennas could we possibly use in a VLBI observation around the world? And we started listing them off and came up with 18 telescopes that would work at 18 centimeters wavelength. And it led to a project which we called the World Array. It took well over a year to correlate all the data from a few days of observation, because you had to correlate over 150 baselines with a correlator that could handle 3 baselines at a time. So you can imagine how slow that is. Well, what do we see? For M87, oh, sorry, this is the list of telescopes that we used. It's painful to look in the middle there and see Arecibo, which doesn't exist anymore. Yeah, it died on my birthday last year, so that was great. But what did we see? Well, this was the image that was made for M87, and it was really one of the prettier images of VLBI images ever made at that point. It was really the first image that resolved an AGN jet across the jet axis, perpendicular to the flow direction. It showed some very interesting properties. It looked like it was limb brightened with sort of a helical pattern going on through it. That suggested that there was a central fast spine possibly, and then a sheath around it, which Roger talked about in his talk. No counterjet was seen in this higher dynamic range image than the previous one I showed, to a limit of about 200 to 1 in brightness. And knots in that jet were seen to move actually quite slowly, only 0.3 C or so. And this was in contrast to almost all quasars that people had mapped with VLBI at the time, where you would see superluminal motion instead of subluminal motion. Turns out it was fairly hard to explain all the observations of M87. And here's sort of a plot in our paper. It's plotting on the vertical axis the sign of the angle of the jet with respect to the line of sight. So if it's 0, it's coming right at you. If it's 1, it's in the plane of the sky. As a function of beta here, which is the flow speed, the bulk flow speed of material in the jet, going from 0 to the speed of light 1. The one-sidedness of the jet, if that came from Doppler boosting, restricted one to this region on the right-hand bottom right of the plot because of the brightness limit of the ratio of the jet to the counterjet. The subluminal motion, very slow motion, puts you on a track that's given by that hatched pattern I just highlighted. And we added one other constraint, which was that further down the jet than we're seeing, as seen in VLA images and later in optical images, is not A, it's called. And it has a very sharp, bright, linear feature that exactly crosses the jet. And it looks like a Mach disk or something like that, viewed edge on. So if you account for relativistic aberration, you find yourself somewhere in that stippled region in there. And you put them all together, you could not satisfy all 3 constraints at all, except at the trivial point, beta equals 1 and sine theta equals 0. We pointed out fairly, I think even in this paper, we were a little concerned about the subluminal motion. And basically much more recent observations, including, for example, the stuff Craig Walker has done at much higher frequencies at 43 gigahertz, indicates that you can get much higher apparent motions of knots and structures in the jet. It's also seen optically, and they actually go up to about 6 times the speed of light for an apparent motion. So you rule out the subluminal motion plot constraint, and you end up with the region with the smiley face there, where things probably should be for M87, and I think that's pretty well within what people now think. For example, it gives an angle to the line of sight of between 15 and 20 degrees or so. Okay. So let's move on to my second love affair, and that's been Sagittarius A star. So in the 1990s, I actually had wanted to try to measure a trigonometric parallax to Sag A star. So we started observing it, and we measure Sag A star against a background quasar. And basically it was a long period of learning how to do this more accurately. And what we got is the data on the right there, and that's the sky with the measurement in 1995 at the top and 2013 at the bottom. You can see it moves a long way. Ironically, Sagittarius star is a bad parallax target because of the scattering. And so even at 1 centimeter wavelength, this is actually done at 43 gigahertz, at 7 millimeters wavelength. It's still scatter broadened, and you really can't use very long baselines to do this. But you can get a very accurate proper motion, as you can see here. And proper motion uncertainty decreases as 1 over the square root of 3/2 power of time. So it really gets better with time very quickly. An interesting point here, if you just look at it, Sagittarius star appears to move by 16 micro-arcseconds per day. So that's about an EHT beam in 1 day. So it actually moves considerably even while you're observing it, which is kind of astounding. If you fit the red line, the dashed line, that gives you Sagittarius star's apparent proper motion. And what is it? Why is it there? Why is that there? And this is basically what's happening. Here's a schematic looking down on the galaxy with Sagittarius star at the center and the sun at the top. And as the sun goes around in its 200 million year orbit, when you view Sagittarius star, a nearby source, against distant quasars, it appears to move. And the measurement that we get from the fit from that red line is that the angular motion, which is the linear motion divided by the distance to the galactic center, is 30.24 plus or minus 0.12 kilometers per second per kiloparsec. So you get about 1/3% accurate estimate of its angular motion. It turns out this is all from the sun's motion. And in fact, here's an independent measurement, which I'm going to show you in a minute. So this is a little out of order, but you need this number. That the same angular motion you can measure from parallaxes and proper motions of stars throughout the Milky Way. And you get essentially the same number from that. And so if you difference those two numbers, you get that at least the in-plane motion, intrinsic motion of Sagittarius A star is near 0. It's of order 1 kilometer per second, in this case about 2 kilometers per second uncertainty. You can also get the out of plane motion, which is actually the reason the blue line, which is the galactic plane, and the red dashed line aren't exactly on top of each other. That's because the sun is moving out of the galactic plane at about 8 kilometers per second. After you subtract that from the data, you get that the out of plane motion is about 1 kilometer per second limit also. So how fast should Sagittarius star be moving? So it's intrinsically moving of order 1 kilometer per second or less, very, very small. Well, it's got a cluster of stars around it that are bound to it actually, and those are going to perturb it. And it's basically a gravitational Brownian motion problem. And you can, from that, expect that you would see motions of order a few tenths of 1 kilometer per second. So actually we're pretty close to measuring about what you'd expect from a 4 million solar mass black hole being kicked around by a few million solar masses of stars that are bound to it. So we can actually then try to put a lower limit on Sagittarius star's mass, the mass of the radiative source, by running trials of a stellar cluster. You set up a stellar cluster like that randomly. You give them random orbital elements. You evolve the orbits for the 18 years that we've observed it here. And you'll find that all the stars are in a slightly different position. So you calculate the difference in the center of mass of the stars at time 0 and time 18 years. And it's going to be a little different randomly. That's the, and in this closed system, the simple closed system, that's the reflex of the motion of Sagittarius star. And so, for example, if Sagittarius star were a low mass X-ray binary, which it could be from luminosity arguments, it's a very wimpy source, it would be moving at thousands of kilometers per second at that position on the sky, which is as seen in other stars. And if it's a 4 million solar mass black hole, then it would be moving very slowly. And so you can put a limit on that. So what we do is we'd run these trials. You can just do thousands of trial stellar clusters and compare the motion you see in 2 dimensions with the motion we measured, and we can draw it from the same distribution. And we find that if Sagittarius star were a 4 million solar mass black hole, which it probably is, 80% of the time we wouldn't detect it, 20% of the time we would detect it. If you drop the mass of Sagittarius star down a little bit to 1 million solar masses, we would have detected it about half the time. And so that's basically a pretty good lower limit for the mass actually tied to Sagittarius star. So, and I just point out, this is an extremely conservative calculation. We're ignoring any possible clumping, and we're ignoring any stellar remnants in the galactic center, which would kick Sagittarius star around a bit more. It should move faster then. Well, what can you do with this number? Okay, so here are density calculations based on 4 types of objects. The top line is for a globular cluster, just as a reference. It's 1 million solar masses, say, within a radius of 1 parsec, or 2 × 10⁵ astronomical units. If you look at the right-hand column, that's the mass density in solar masses per cubic parsec. It's a bit over 10⁵. And we, of course, know that globular clusters are mostly composed of stars. The stellar orbits measured in the infrared, for which Goetz and Genzel got the Nobel Prize last year, constrains things to be 4 million solar masses within a radius of 100 astronomical units. That's basically the pericenter of the closest stars that they've observed. And that gives a whopping mass density of more than 8 × 10⁵ solar masses per cubic parsec. And that's, of course, extremely strong evidence for a supermassive black hole. It rules out almost anything you can think of, and that's why they got the Nobel Prize. But you can actually push this further. Sagittarius star's motion, being very small, constrains its mass to be greater than 1 million solar masses. And the observed radius of Sagittarius A star is about 2/10 of an astronomical unit from many observations, including probably ngEHT observations, early ones for sure. And that gives you a mass density of greater than 4 × 10⁵ solar masses per cubic parsec. And if you take a generic non-rotating supermassive black hole, the density within the innermost stable orbit of 3 Schwarzschild radii is not much bigger. It's about 6 × 10⁵. So putting this all together, this provides absolutely overwhelming evidence that you're looking at a black hole there. And if it's not a black hole, then I always say the physics is even much more interesting. Well, let me go on to one of the other loves. I've been trying to map the Milky Way with micro-arcsecond astrometry now for about 15 years. And here's a galaxy that actually may look quite a bit like the Milky Way. It's UGC 12158. And if the sun were where that yellow dot is that I just put up on the screen, and if you find a high mass star forming region, say the one I've circled there, and if you could measure a trigonometric parallax, you get a distance and you locate it. And you just do this for lots of them, and you trace out the spiral structure of the galaxy. So our target sources here are astronomical masers. These are found around young, very massive O stars, so that they're really good because those trace spiral structure very well. We're looking at clouds of gas that are sort of solar system in scale and Jupiter in mass. And these clouds have water masers and methyl alcohol masers. And the nice thing about masers is that they give you very bright spots, which are very good astrometric targets. So here's one example, I don't have much time, of parallax data. This is for a cloud of gas around a very massive young star, very close to the center of our Milky Way, in Sagittarius B2. It's water maser data. On the left, the plot is the sky, and it shows you over 1 year, the source started at the top and moved down toward the bottom with a little wiggle in there. The second panel breaks it up into right ascension and declination motions as a function of time over 1 year. And the blue line is the right ascension direction, which turns out to be the critical one here. If you remove the proper motion, you get the plot on the right, and that it reveals the effect of the Earth's orbit of trigonometric parallax. And you can see we have a very clear detection of a parallax in the right ascension data. The declination data, basically the way the Earth's orbit appears to the galactic center is it's edge on by coincidence. And so all of the astrometric signatures in the right ascension direction. So we've measured, well, in this case, we get a parallax. The parallax is 129 plus or minus 12 micro-arcseconds. And so you invert that number, convert it to milli-arcseconds and invert it, and you get a distance in kiloparsecs. So it says the Sagittarius B2 is at 7.8 kiloparsecs with about 10% uncertainty. And that's actually a pretty good estimate of the distance to the galactic center directly, but it's not terribly competitive with what we can do putting all our sources together. So there are two groups who are doing this. We're doing this with the VLB array, and there's a group in Japan that have a dedicated array of 4 telescopes called the Vera array. And between us, we've measured about 200 parallaxes to massive stars. And here's a schematic of the Milky Way showing all these sources. The galactic center is at 0, 0 at the center, and the sun is up partway to the top with the red sun symbol there. So that's where we are. We've color-coded the sources mostly not using the parallax data. That is, we didn't use the location to color code them. We used carbon monoxide longitude velocity plots, which are, there's a little picture there on the right. And basically you can see spiral structure clearly in those longitude velocity plots. What you can't do from those plots, what you can do is assign them to a spiral arm in those plots. What you can't do is know where the spiral arms are, and that's what we're doing here. It's been kind of fun. I don't have time to talk much about this, but the black dots are the Perseus spiral arm, and it's thought to be one of the dominant spiral arms in the Milky Way. But if you look at it, you know, there are a lot of sources in quadrant 2, which are right here, and a bit in quadrant 3. But as you get into quadrant 1, as you go toward the center of the Milky Way, as you wind in, there are very few spots, very few sources. It turns out the Perseus arm has a huge gap in it with very little star formation. So it may not be such a dominant spiral arm if we could get outside the Milky Way and look back at it. The points in cyan are the local arm because it's local to us. That was thought to be an insignificant little spur. Turns out it's a pretty dominant arm segment that's just floating around there in the Milky Way. You can model the 3-dimensional velocities we get and solve for the fundamental parameters of the Milky Way. The distance to the galactic center, R0, down here at the right, and the circular rotation speed of the galaxy at the sun, 236 kilometers per second. This is how I got that angular rotation rate that I used in the Sagittarius A star discussion, which is down at the bottom. Okay, well, now that we know along any one of these spiral arms, we know where that spiral arm is, and we know the line of sight Doppler shift along the spiral arm from all the sources. What we can do is we can go to catalogs of sources that have longitude, latitude, and line of sight velocity listed. And we can then try to pair them up with a spiral arm in a probabilistic sense and end up with a really good estimate of distance, much better than any other method of doing it from that. And when you do this, we've taken 4 catalogs of star-forming region sources. They're listed there on the right, and dumped them into this Bayesian program, which on a probabilistic basis assigns them to spiral arms and tries to estimate distances that way. And the blue points on that figure are the ones where it was pretty confident, and the cyan points are ones where it was not very confident. And that's probably, I would say, the best direct visualization of what the Milky Way looks like. Of course, we give this to an artist and tell him to make it look something like what a galaxy looks like. and you get back that image. And so that's probably the most scientifically accurate artist's conception of the Milky Way that exists now. Okay, well, in the last 5 minutes or so here, I'm just going to go through and talk about some thoughts on VLBI and ngEHT astrometry. You know, what can you do basically, and where are the limitations? And so for the VLB array pictured there, the angular resolution at 1 centimeter wavelength gets down to about 300 micro-arcseconds. And of course, you can get a precision that's much, much better than that of the centroid of a nice bright spot. So with sufficient signal to noise ratio, you can get down to a micro-arcsecond rather easily, actually, in precision. But it's all about systematics. And here's a great street sign in my neighborhood. It says West Street, formerly known as North Road. And that's a systematic error of 90 degrees. So every time I drove by that, I just sort of laughed. Okay, well, what's limiting us? Astrometric errors at VLBI at 1 centimeter wavelength. So we have telescopes. We're looking at a target source given by this funky symbol here. And we nod the telescopes against the background quasar to get absolute position information. And after you take care of, you know, all the little things like where the telescopes are and tides and UT1, UTC corrections and things like that, what you're really left with in the end, usually, is the Earth's atmosphere, and actually water vapor in the Earth's atmosphere at 1 centimeter wavelength. And so you have little sort of cloudlets that drift by the telescopes on time scales of minutes, and you sort of have the whole big picture on the time scale of hours, which is basically how much water vapor you didn't account for that's above each telescope that you have to take into account. The fast moving stuff, the minute scale stuff, is what's responsible for short coherence time in the interferometer. And you know, it's typically about 1/10 of a centimeter path length noise over a few minutes. And you can remove most of that by phase referencing rapidly between the two sources. The hourly stuff is actually more critical for the astrometry. Basically, if you don't do anything fancy, you'll have about 5 centimeters of residual path length or path delay in your data. Now you can remove that by what we call geodetic-like calibration, where we basically cycle around the sky quickly, looking at a lot of quasars whose positions are well known, and basically looking for the secant zenith angle effect as in delay in the atmosphere as you pierce more and more air mass. And from that, you can remove most of this effect down to about 1 centimeter accuracy. And it turns out 1 centimeter is a fringe at 1 centimeter. And that's about 300 micro-arcsecond absolute error. However, that stuff will cancel roughly as the separation between your two sources converted into radians. We typically find a background quasar near our target in angle to within about 1 degree or so on the sky at current sensitivity limits. So we cancel by about 1/57th of a radian, and that gets you down to about 10 micro-arcseconds for our accuracy. Okay, what happens if you try to do this at 1 millimeter wavelength? Okay, so for EHT now. So the stuff that goes by on minute scales that leaves about a 1/10 of a centimeter or about 1 millimeter residual, that's going to actually decorrelate you for the EHT. And so you'd have to go to faster time nodding. You'd have to get probably down to tens of seconds or less in order to get rid of that decorrelation. So that's not easy to do. That's one potential problem. Now, if you have 2 telescopes at each site, that you can be monitoring both continuously, and then you don't need to switch, and you can take out a lot of this effect. And there's a paper by Avery in 2011 on this whole thing, and I highly recommend that paper. I helped a little bit with it, but not much. One thing, when you do take out all the temporal fluctuations, you still have to deal with spatial fluctuations, but those tend to be a little easier to deal with than the temporal ones, and you have to read the paper to see it. Okay, so let's go on to the hourly, the large scale structure in the atmosphere. And
Mark,
yep.
just to, we're at the end of your time. Are you close to wrapping up?
About 1 minute away.
Great.
Okay, so you could ask the question, does angular resolution help you? You think at astrometry, angular resolution helps. This is actually an interesting little thing here. So the astrometric error you get is basically a fringe spacing, which is this lambda over the baseline length, times a delay error converted to a path delay by multiplying by the speed of light and dividing by a wavelength. So basically a path delay error of 1 wavelength gives you a 1 fringe error. But you'll notice the lambdas cancel here. So it's not angular resolution that, gaining angular resolution by going to shorter wavelength does not help you for astrometry like this. And so all that counts is your magnitude of your delay error, which you can, hopefully improve on by having a better sight, or your baseline length. That's what counts. So what you can do is go to space and get rid of the atmosphere. And that's great. But this will only help for space baselines. Well, it will only help the most. And the other thing that will pop up, of course, going to space is that if you don't know your antenna locations to this magic 1 centimeter number that I've been talking about, you won't do any better than the astrometry from the ground. So you're going to have essentially the metrology good to better than 1 centimeter if you want to do EHT from space and do astrometry better than you do from the ground. And I think I'll quit there.
Great. I'll do the applause for everyone. Thank you very much for fascinating talk. We're into the coffee break. And I know the organizers want to keep us on time, but we can take some questions during the coffee break here, at least for a few minutes before we start up again at the quarter hour. So I see Haub has his hand up.
Yeah, Mark, we're all very keen, of course, to do 1 millimeter and SIO maser astrometry. You didn't reflect on the possibility to do phase transfer between frequencies. And
yeah, no, that's been well demonstrated, and that can help you with a coherence problem, definitely.
Okay. Point taken, point made.
Yeah.
Okay, I don't see other hands, so I'll take my prerogative and ask. So, Mark, you've been involved in the design development of many ad hoc and dedicated VLBI arrays through the decades. What insights, what advice can you give on the process and how to make that work?
Well, I can certainly say that there's a lot more than you think to getting an array working. I'm trying to get an array working in the Southern Hemisphere, and it has to be a dedicated array. If you want to do parallaxes, we need 1,000 hours a year of observations. So, for example, the Australian long baseline array, which does VLBI, won't work well for that. So I'm putting together a new array. I thought it was going to be really easy. The University of Tasmania in Australia owns 4 telescopes spread across Australia to do geodesy. So they've been doing VLBI. I said, this is going to be easy. Just throw a new receiver on there, some new electronics, and get going. Of course, I've been used to the VLB array and NRAO, where they have outstanding staff to make things work. Turns out these 4 telescopes that are run by 1.5 people across a continent. And so it's been an adventure trying to get all this stuff put together and working and things like that. So it's the little things, I think. So standardized antennas and electronics would certainly be a very important thing.
Okay, great. Well, I think we want to give everyone the opportunity to take a break here. Thanks again for your terrific talk, Mark.